Guys, in this video we're going to be focusing on finding the zeros of a polynomial function. And so just to be very clear on this, what the heck is a zero? We say that if f is any polynomial function, then the values of x that we plug in that would cause f of x to equal 0, those are called zeros. So just to be clear on this, they are x values that when we plug them in, we get 0. So here's the definition of a 0. It's all of the x values that basically cause our y value to be 0. So another name for a 0, if we're going to be clear on this, is, well, I suppose if I had some polynomial function where I was finding the x values where our y value was 0, it would be all of these points right here. And so in other words, we could say that a 0, another name for this really is an x-intercept. And that's what we're going to be interested in finding here. We're going to be interested in finding any x-intercept of our graph or any 0 of our graph. And so I'm gonna put some points up here. I'm gonna call this x1 0, I'll call this x2 0, and I'll call this x3 0. But just to be clear, these are x values that when we plug them in, we get zeros on our function. So yes, the x-intercepts are the same as zeros. We also refer to these as the roots of the solution, or roots of the equation, the solution of the polynomial equation f of x equals 0. So basically what we want to do in this video is to find all of the zeros for each of these polynomial functions that we have listed here, and then also give this thing called the multiplicity for each 0. Lastly, we want to state whether the graph crosses the x-axis or touches the x-axis and turns around at each of our zeros using that word multiplicity. So let's just start with the zeros here, at least with number 25 here. The fact of the matter is, if we're finding the zeros, another name for this is just an x-intercept. So how do we find an x-intercept? Well, to find an x-intercept, you set y equal to 0 and solve for x, because we know our y values would be zeros at our x-intercepts. And so that being the case, we'll say on number 25 here, I'm going to plug in a 0 for my f of x, or my y, and I'm going to say this is equal to 2 times x minus 5 times x plus 4, and that's x plus 4 squared. So I'm going to say another way that I could write this here is x plus 4 times x plus 4. And I'm going to go back to this notation here in a second. But basically what I want you to see is, well, first of all, number 25, whoever gave us this did us a huge favor because, well, the way we solve polynomial functions is to set it equal to 0 and factor it in the first place. And so because this is already factored out here, the initial expression, we see that 2 times x minus 5 times x plus 4 times x plus 4 here. I want to know, what would x values have to be here for this to go to 0? So what I want you to notice first of all is that this 2 isn't going to have any impact on what x should be to cause this to be 0, because there is no way in the world that 2 is ever going to be equal to 0 here. So when we factor this out and solve it, our practice really is to take any factor that's bearing an x, that has an x in it. And what we're going to do is say, well then, if everybody here multiplied out to be 0, if this times this times this times this is 0, then either x minus 5 had to be 0, or x plus 4 had to be 0, or x plus 4 had to be 0. So the interesting thing here is we can very easily solve these here. We would say that our zeros, or our roots or solutions or x-intercepts, would be x equals 5, x equals negative 4, okay, I'll put a box around this, and x equals negative 4. So you'll notice that we actually got the same answer twice. So what does this mean? Well, what it means is we're going to be using this word multiplicity now. So just to be clear, multiplicity, if you want to know what multiplicity tells us, multiplicity is a fancy word for, I guess it tells you the number of times each solution occurs. Okay, just to be clear on this. So as we look at this over here, well, we solved it. It was already factored. We set y equal to 0 and we found our x values here. So our x-intercepts are these, but we would say x equals 5 has a multiplicity of 1. And I'm going to abbreviate here. We say mult of 1. And so x equals 4 here, we would just say x equals 4, and right next to it we would say mult of 2. Now, why would I do this instead? Well, a couple of reasons. First of all, so you don't have to write it twice. As a matter of fact, we could have just said we get negative 4 for a solution twice, okay? And the other reason why we write this is because it's going to have a direct impact on how our graph behaves here. So before I look at the graph of this, one thing I do want you to notice before we move on here is basically this. If you're already factored, at least factored in a simple form like x minus or plus a number, then you'll always be able to see that if this is your factor, say x minus 5, then x equals 5 is going to be your 0. And that's easy to check. If you put a 5 in right here, you get 5 minus 5 is 0. And also over here we say if x plus 4 is a factor, well then x equals negative 4 is the 0. So let's go ahead and do this. Let's actually go graph this here. We have 2 times x minus 5, so f of x equals 2x minus 5. Now, first thing I want you to notice is this. I'm going to zoom in a little bit here. Because my only factor is x minus 5, currently this polynomial has only one x-intercept at positive 5. When I build in my x plus 4, I know I don't have this foiled out, but if you did, you would have some parabola, like the one we have right here, and you would have 2 zeros. Of course, you would have one at positive 5 for this factor, but you would have one at negative 4 for this factor. Now, what I want... undo. What I want you to notice is that right now, of course, these are our only 2 factors, so there are only 2 zeros. If I were to go up here and repeat my x plus 4, I still get an x-intercept at negative 4. You guys, I still do. But here's the deal. You notice that your graph did not cross the x-axis this time. Well, why is that important? Well, let's keep playing with this. What if I add in one more x plus 4? That would mean, you guys, we would get negative 4 with a multiplicity of 3. Now my graph crosses. What if I were to add in one more x plus 4? Now I get a multiplicity of 4, and my graph still touches here, but it doesn't cross. And so in order to kind of abbreviate this, you're going to start to see that we tend to use a notation like this. I get the answer twice, I get the answer 3 times. I get the answer 4 times, I get the answer 5 times, 6, 7, 8, 9. What I'm seeing is that every time we have an odd multiplicity, then our graph actually has to cross at that x value. And every time we have an even multiplicity, like if I got this answer 8 times, my graph would have to approach the x-axis, touch it there, but flatten out and turn back around. Okay? So just to be clear on this, we say that multiplicity and x-intercepts, if r is a 0 of even multiplicity, okay, that would be saying something like this. X minus r is our 0, so x minus r is our factor. If it has even multiplicity, so I'm going to say to the k here, where k is even. Let me fix that. We'll just write k even, you guys. K even, we say no cross. Doesn't cross, okay? And if we had x minus r to the k, where k odd, okay, we get the same answer an odd number of times, an odd multiplicity. It crosses the x-axis at that point, okay? And so what I want to be able to do is easily solve for zeros, you guys, but also state how many times we get each 0, so that we can say things like determine whether the graph crosses the x-axis or touches the x-axis and turns around at each 0. So to go back to number 25 here, we would say multiplicity of 1. That means that we're going to cross the x-axis at that point. But because we have an even multiplicity here, we're going to say no cross, it doesn't cross. So let's try this again here. I want to try this. Actually, we can do this a little bit more quickly this time. Number 27 here. Why don't we pick on it? And so number 27, we want to find the zeros of this function. Remember, those are the x values that when we plug them in, we get 0 for y. So in order to find this, the zeros, the x-intercepts, we just set y equal to 0 and we solve for x. And so to solve this time, what I want you to see is a little bit different than we're going to look at how we did it last time. I'm not going to write x plus 6 times x plus 6 times x plus 6. But what I am going to say is that I get x minus 3 equal to 0. And over here I get x plus 6 to the third equal to 0. So when I solve this, what you're going to find out is that I get 3. And what I'm going to write underneath this is that I get it once. Multiplicity of 1. Now over here, I know that I'm going to get negative 6 each time. I know it when I set x plus 6 equal to 0 3 times, I'm going to get negative 6. But when I put a box around this time, I'm going to write multiplicity of 3. So to assess the situation here, the fact is that these both have odd multiplicities. So with respect to does our graph cross or not cross there, remember that our graph will cross if it has an odd multiplicity. And so those two, 25 and 27, very interestingly, were already factored for us. Why don't we take a look at one that is not already factored for us? So for instance here, number 30. That's right, I said number 30. So number 30, taking a look at it, we say here's our function. We want to go find the zeros of this function. So what we're going to do is, since we're finding x-intercepts, we're going to plug in 0 for y, and we're going to go solve this. The thing here is we have to solve this most of the time by factoring. And so factoring wise, we always look for what first? I mean, looking at all these terms, do you notice anything that they have in common? I notice that they have an x in common. So I'm going to factor out my x, and what I get left with is x squared plus 4x plus 4. Now, it's my duty, my due diligence to say, could I keep factoring this? And as a matter of fact, I hope you recognize that this is entirely factorable. We see that two factors of a positive 4 that add up to be a positive 4 would be x plus 2, and as a matter of fact, x plus 2. So one thing that I'm going to encourage you to do as we get used to factoring more heavily here is if we have a repeated factor like this, let's actually list it as x times x plus 2 twice. And so that when we set now each of our factors equal to 0, we could say, well, I get 0 with a multiplicity of what? Well, of 1. We only got 0 for an answer once. And I get x plus 2 is our factor if and only if x equals negative 2, that would equal 0 if negative 2 was our x value. So we would say that this has a multiplicity of 2. And that would be very easy for us to go look at just this exponent right here to tell us what its multiplicity might be. So to look at this graph, x cubed plus 4x squared plus 4x, would we expect it to cross or not cross at these zeros here? What I would see is that because this is an odd multiplicity, it crosses. And because this is an even multiplicity, we have no crossing. Okay? And so I do want to go take a look at this graph, as a matter of fact. I do want to go graph x cubed plus 4x squared plus 4x. So x cubed, we say f of x equals x cubed plus 4x squared plus 4x. And what you're going to see is that we definitely have these two zeros. That was unmistakable that we had those once we factored this out. But at negative 2, as we mentioned here, because we got that answer twice, we got a graph that came, flattened out, touched, and turned around at the x-axis. Instead of doing what it did here at 0, which we got as a multiplicity of 1, it actually crossed at that 0 right there. So what I want you to try now is just say for something like number 31 or 32 there, let's set our y value equal to 0 and solve for x by factoring, but make sure you note how many times you get each 0 for an answer and whether or not that would cause your graph to cross at that x value. Cheers.